So let's think about this for a second. How does all that power, I mean immense power, from a massive power plant make it safely to the tiny outlet in your wall? It's this wild journey where the electricity's voltage gets cranked up hundreds of times and then, right at the end, dialed way back down so it's safe for your home. So what's the trick? How do we pull that off? Especially with a device that has zero moving parts.
Well, the answer is a device that's both super essential and, honestly, pretty elegant, the transformer. And that's exactly what we're diving into in this explainer. We're going to unpack the science and the engineering behind this quiet hero of our modern world. Okay, so here's the game plan. First, we'll get into the basic principle, how it all works. Then we'll look at how they're actually built and the problem of energy loss. After that, we'll check out how we measure performance. And to wrap it all up, we'll zoom out and see how transformers fit into the bigger picture of the power grid.
All right, first things first, let's get right to the core of it, the fundamental science that makes the transformer even possible. So what exactly is a transformer? Well, at its heart, it's this electrical device that does one thing, and it does it incredibly well. It changes the voltage of an alternating current, that's AC, either bumping it up or bringing it down. And the really crucial part, it does all of this without messing with the electricity's frequency. Okay, so what's the secret sauce? The real magic here is a principle called electromagnetic induction. It's this amazing phenomenon where a changing magnetic field can actually create an electric current in a totally separate wire nearby. And the key is, there's no physical contact. It's like action at a distance. And that's the whole trick that makes a transformer work. And get this, the way it's controlled is so simple, it's brilliant. You want to step up the voltage? Easy. You just make sure you have more turns of wire on the output side, the secondary coil, than on the input side. And to step down the voltage, you guessed it, just do the opposite. It's this beautiful, direct link between how you build it and what you get out of it. And this whole relationship is summed up perfectly in what we call the turns ratio. It's a simple little formula, but it's incredibly powerful. It just says that the ratio of the voltages is the exact same as the ratio of the wire coils. But, and this is a big but, there's always a trade-off, right? When the voltage goes up, the current has to go down. You can't create energy out of thin air. You can't get more power out than you put in. This balancing act is really the key equation that governs the whole thing. Okay, so that's the theory, right? Pretty elegant stuff, but how do you actually build one of these in the real world? Let's take a look at the actual construction and some of the real-world challenges engineers have to deal with, like energy loss. So you'll mainly see two types of designs. You've got your core type, where the copper wire windings are wrapped around the iron core. Then there's the shell type, where the iron core is actually built to surround the windings, kind of like a shell. They both have their pros and cons. The core type, a bit easier to insulate and repair. The shell type, on the other hand, gives you better mechanical protection for those super important windings. Look, nothing in the real world is 100% perfect. Transformers are crazy efficient, but they still lose a tiny bit of energy, mostly as heat. And these losses basically fall into two big buckets. You've got the losses happening in the iron core itself, and then you have the losses happening in the copper wires. All right, let's dig into those core losses for a sec. They come from two main things. First, there's something called hysteresis loss. The easiest way to think about it is like bending a paperclip back and forth really fast. It gets hot, right? That's wasted energy. The iron core is doing the same thing, magnetically speaking, and it heats up. Then you've got eddy currents. These are basically tiny, unwanted little whirlpools of current that swirl around inside the core, and yep, they generate even more heat. But the solution engineers came up with is just brilliant. They build the core out of a stack of thin, insulated metal plates called laminations. This design totally breaks up those little whirlpools and slashes the energy loss. So how much are we talking about here? Well, when a transformer is running at full load, it's the copper losses, the ones from the current flowing through the wires, that are usually the bigger problem. They often make up about 60% of all the energy that gets lost. Okay, so this brings up a really important question. If transformers aren't perfect, how do we know how good one is? How do we measure it? Let's check out the tests and the numbers that define their performance. So how do you actually separate and measure these two different kinds of loss? Engineers have two really clever tests for this. First, they do what's called an open circuit test on the low voltage side. This is perfect for isolating and measuring those constant iron losses. Then they do a short circuit test on the high voltage side to figure out the copper losses that happen when it's working its hardest at full load. You run both of those and boom, you've got a complete performance profile for that transformer. And why do we do these tests? Well, they let us calculate the single most important number:
efficiency. And modern transformers are just incredible. We're talking efficiencies over 99%. And that might sound like it's almost perfect, but that last little percentage point, it matters a lot. Think about it. Across an entire country's power grid, just a 1% gain in efficiency can mean we don't have to build an entire power plant. That saves millions of tons of CO2 and literally billions of dollars. It's huge.
So, is there a point where a transformer is working at its absolute best? Yup, there is. There's a sweet spot. Remember we had the constant iron losses and the variable copper losses? Well, a transformer hits peak efficiency at the exact moment when those two losses are equal. It's his perfect balancing act between its two types of imperfections.
Another really important number to look at is voltage regulation. All this tells you is how steady the output voltage is. Does it dip or sag when you put a big load on it? A smaller number here is way better. It means you're getting a nice, consistent, reliable voltage coming out the other side, which is exactly what all our electronics need.
All right, we've been looking at the device itself, but now let's zoom out. Let's see how these things come together to form the actual backbone of our entire electrical grid. Okay, on the big grid, power isn't simple. It's three-phase. And to handle that, transformers have to be connected in special ways. The two you'll see most are for stepping voltage up and down. Right at the power plant, they use a star-delta connection to jack the voltage way, way up for efficient long-distance travel. Then, when that power gets to your neighborhood, a delta-star connection brings it all the way back down to a safe level for all of us to use.
So remember all that talk about energy loss? Well, all that lost energy turns into heat. For the smaller transformers you might see on a pole, just letting air and oil circulate naturally is enough to cool them. But as they get bigger and handle more power, you've got to get more serious. You start seeing fans for forced air, and for the really huge ones, they even have pumps to force the cooling oil to circulate, just to keep them from overheating. So what happens when you need more power than just one transformer can give you? Well, you can hook them up to work together, in parallel. But the rules for this are super strict. They have to have the exact same voltage ratio, the same impedance, the same phase. Everything has to match perfectly. Think of it like a rowing team. For the boat to go straight and fast, every single rower has to be pulling with the exact same strength and at the exact same time. It's the same idea here. They have to be perfectly in sync to share the load. So when you really think about it, from the moment electricity is generated to the second you plug in your phone, the transformer is there at every single critical step. It's this silent, steady, unmoving workhorse that makes the whole system possible, letting us send power over huge distances and then making it safe to use. Which really just leaves us with one final big question. Without the transformer, could our modern electrically powered world even exist at all?